Have you ever thought about how amazing elevators are? We'd understand if you hadn't, because they're so easy to take for granted. Going up and down lifts doesn't feel like a bigger deal than taking the stairs, and yet this one invention has shaped the present and future of modern architecture. In this video, we're going to take a look at this invention, how it works, and what potential it might still hold. First up, humans figured out the need for lifts a long time ago. The earliest concept for an elevator was dreamt up and built by Archimedes, the legendary Greek physicist and engineer. We don't know much about how this lift worked or what it was used for, but this was first reported by a famous Roman architect, the one and only Vitruvius. Now, in those days, there were no such things as high-rise buildings, so the use or need for modern elevators simply didn't exist at the time. But construction sites, mines, farms, and other backbreaking areas of work really needed a way to transport things up heights. You've probably seen the famous illustrations of workers up on the pyramids, rolling stones, and other materials on carts up slopes. Speaking of the Romans, the first example of an actual working lift comes from the Colosseum, which was completed in 80 AD. Funnily enough, the lifts weren't created for construction purposes, but rather for transporting animals up and down. There are 25 of these lifts, and each one could carry about 600 pounds to a height of 23 feet. The Romans didn't wait for variable frequency drives to be invented, so these lifts had to be pulled by a team of 8 men. Let's fast forward to the Industrial Revolution when mechanized lifts finally emerged. By the 19th century, technology had progressed to a point where steam power could be used to make an automatic elevator. This was good timing, as the rigors of the industrial world made elevators essential for increasing efficiency and productivity. The first steam-powered elevators were installed in coal mines in the 19th century, while Burton and Homer, two London architects, showed off the concept of an elevator to tourists. As the century wore on, the technology behind elevators started to get better and better. In fact, the lifts we use today are very much rooted in design principles from this era. Lifts weren't just good for mines and factories, though. The Industrial Revolution created another problem that was solved by these lifts. People were moving en masse out of the countryside and into major cities and industrial hubs, increasing the population density of those areas. You could only build so many homes for them, but this is when architects had the bright idea to build homes in a vertical stack, also known as a residential high-rise. If a high-rise has just a handful of floors, a staircase would be enough. But as these buildings got taller, stairs became less practical. Luckily, lifts were now refined enough to install in these buildings, and that's how your everyday lifts came into being. Now that our history lesson is out of the way, what are the fundamentals of elevator design? If you wanted to break down elevators to their most basic design, they are basically potential energy exchangers. That doesn't sound very basic at all, but we'll tell you what that means. Potential energy is the energy that is gained when an object moves from altitude to a higher altitude. When you go up the stairs, you're basically gaining potential energy as a result of working against gravity. Lifts also go through the same process to move the metal box, known as the cabin, up and down. But if all you had was the cabin attached to a pulley and a motor, that motor would have to do an insane amount of work to pull the lift up. We know from experience that lifting heavy objects is rough. That's why the cabin needs a counterweight. Imagine two equal weights that are connected by a pulley, and they're at the same height right now. If you pull one weight down, the pulley will pull the other one up, and vice versa. This won't require much effort from yourself at all. The reason for this is that when one weight goes up, it gains potential energy, while the other weight loses potential energy. So the entire system isn't actually gaining or losing potential energy at all. It's just being traded between the two weights. We hope we just triggered your eureka moment, but don't do what Archimedes did when he had his. If you scale the weights up to an elevator cabin and an equivalent counterweight, that's what a lift is at heart. Moving on from the basics, we'll look at the specific components of an elevator. We've covered the cabin, the counterweight, and the pulley. The truth is that lifts aren't much more complicated than that. The stuff we talked about before has a bit of a caveat. It assumes that the weight and the counterweight are equal. But while the counterweight, which in reality is a big metal rod, is constant, the cabin's weight changes. Its weight is different when empty, and it'll increase when there are passengers inside. That can complicate the potential energy exchange between the two, and the pulley might need some help. Our example so far also assumes that the elevator only has 2 destinations, but in a building there can be lots of floors, and the lift needs to be able to stop at all of them. Motors will go as fast as the frequency of their input AC power, so to control the speed, starts, and stops of a lift, they usually have a variable frequency drive. Explaining the frequency of alternating current is a topic for another video, but by regulating this frequency, the motor will move as fast as needed and stop as needed. That's going to come down to the programming of the elevator. But elevators can't just stop on a dime. There are brakes that allow the lift to come to a smooth stop at their destination. There's also an emergency brake for when the lift goes into free fall. But here's the thing, you're basically more likely to be eaten by a shark than end up in a free-falling elevator. When was the last time you were scared on a lift? Probably never, and you don't have to be scared at all. The biggest safety feature of a lift is the most simple one. You want to know what happens if something causes a lift to go into free fall? Well, one of the series of cables on the roof of the cabin would just catch it. That, combined with the emergency brake, is plenty to keep the lift safe. That sounds too good to be true, but that system has proven its effectiveness. Across the annals of elevator history, cases of lifts falling down shafts by accident are hard to find. And even when you do find them, there's always an external factor involved. For instance, obviously there were elevators in free fall in the World Trade Center during the September 11th attacks. But before that, the only time a free fall had ever happened was in the Empire State Building in 1945, when it was hit by an aerial bomb. People have died in the vicinity of elevators, but those were largely maintenance accidents. Hydraulic elevators have caused some trouble due to failures of the hydraulic system, but that's why you don't see them around all that much. Before we go, if you were starting to get worried that this video about elevators wouldn't have space elevators, you can relax. Space elevators, for those who don't know, are a super sci-fi idea for a lift that can take you straight to a location in space, like the International Space Station. It's a really interesting idea because once it's up and running, you wouldn't need rockets to go to space anymore. But there are definitely design challenges involved. You can't have a single super long shaft stretching from Earth to orbit, as that thing is bound to collapse and flatten a great deal of the planet. A counterweight is more important than ever in this context, but how do you deal with the shifting potential energy balance when one weight is on the Earth and the other is at the edge of the Earth's gravitational field? There used to be concerns about the materials required. After all, moving through the atmosphere can be tricky, and the air pressure on each segment of the shaft would be different as you move from sea level to space. But some materials have been created that could be right for a space elevator. Carbon nanotubes have some promise in that regard, as do boron nitride nanotubes and diamond nanothreads. You know what though? If you were living in the 19th century, going from the ground floor to the first floor of a building might have been as crazy as going to space on a lift. That really puts things into perspective. We're at a level of technological progress that would drive people from centuries ago insane. Imagine what kind of insane things humans will have achieved centuries from now. That's it for today's video. Give the elevator in your building some love by riding it to the top floor and then riding it down to the bottom. Do you have any questions about lifts and how they work? Post them in the comments section below, and we or one of our viewers will get back to you ASAP. But don't board the lift before liking, sharing, and subscribing.